Hi everyone and welcome to Data Science with Marco. Today we're covering unsupervised learning methods and we'll mainly cover principal component analysis, also called PCA, and clustering methods. As always, we have a bit of theory at the beginning and then we move on to coding those algorithms in a project setting. Let's get started. Let's cover some theory about unsupervised learning. Unsupervised learning is a set of statistical tools for scenarios in which we have features but no targets. This means that we cannot make predictions. Instead, we are interested in finding a way to visualize data or discovering a subgroup of similar observations. Unsupervised learning tends to be a bit more challenging because the analysis is subjective. Also, it's hard to assess if the results are good or bad since there is no true answer. In this tutorial, we will mainly focus on two techniques: principal component analysis, or PCA, and clustering algorithms. Let's cover PCA first. PCA is a process by which principal components are computed and used to better understand data. They can also be used for visualizations. Now, what is a principal component? Well, suppose you want to visualize n observations on a set of p features. You could do a 2D plot of each two features at a time, but that's not efficient and unrealistic if p is very large. With PCA, you can find a low-dimensional representation of the dataset that contains as much of the variance as possible. That means that you will only consider the most interesting features since they account for the majority of the variance. And therefore, a principal component is simply the normalized linear combination of a feature that has the largest variance. You see the equation here, and that should remind you a bit of linear regression. Also, this equation is for the first component. The next one will be in a direction perpendicular to the first one, and the third component will be perpendicular to the first two principal components. In the equation, phi is referred to as the loadings, and they must maximize the equation you see on the screen, and the sum of squared phi must be equal to 1. That's it for PCA. Let's take a look at clustering methods. Clustering is a set of techniques for finding subgroups or clusters in a data set. This helps us to partition the data into observations that are similar to one another, and an application of that could be market segmentation in the context of marketing. We will first explore k-means clustering, which partitions the data in a specified number of k-clusters. And we will also look at hierarchical clustering, which does not need a specific number of clusters. Instead, we can generate a dendrogram and see the clusters for all possible number of clusters. So first, let's focus on k-means. This method simply separates the observations into k-clusters, and we must provide that number k. It assumes that each observation belongs to at least one of the k-clusters, and that the clusters do not overlap. It is important to note that the variation within each cluster is minimized. Here, you can see an example of how the number of clusters will affect how the data is partitioned. Feel free to pause the video if you want to study this a bit longer. Clustering is achieved by minimizing the sum of the square Euclidean distance between each observations in a cluster, as expressed by the equation below. To do so, the algorithm first starts by randomly assigning each observation to a cluster. Then, for each cluster, a centroid is computed, which is a vector representing the mean of the features in the cluster. Then, each observation is assigned to the cluster whose centroid is the closest. The two steps above are repeated until the cluster assignment stops changing. Note that k-means will find a local minimum. Therefore, it highly depends on the initial cluster assignment. So make sure to run the algorithm multiple times to see if you always get the same results. Now, let's learn more about hierarchical clustering. As I mentioned, the potential disadvantage of k-means is that you must specify the number of clusters, and sometimes you simply don't know how many clusters you need. This is when hierarchical clustering comes in because you do not need to specify the number of clusters. The most common type of hierarchical clustering is called agglomerative clustering. It generates a dendrogram from the leaves, and the clusters are combined into larger clusters up to the trunk. Here are examples of dendrograms. We see the individual observations at the bottom, and they are combined into larger clusters as you move up in the y-axis. The algorithm is fairly easy to understand. It starts by defining a dissimilarity measure between each pair of observations, and it assumes that each observation pertains to its own cluster. Then, the two most similar clusters are combined, so there are n-1 clusters. The next two are combined, resulting in n-2 clusters. and so on and so forth, until all observations fall in one large cluster. Although simple, how do we define the dissimilarity measure? That depends on the type of linkage, and there are 4 types: complete, single, average, and centroid. Complete is also called maximal intercluster dissimilarity. It computes all pairwise dissimilarities in cluster A and B and records the largest one. With single, it's the opposite, and we talk about the minimal intercluster dissimilarity. Here, the smallest of the dissimilarities is recorded, and that can mean that single observations are fused one at a time. Then we have average. As the name suggests, the average of the pairwise dissimilarities is recorded. And finally, there is centroid, which computes the dissimilarity between the centroids of cluster A and B. This is sometimes a problem, as smaller clusters can be more similar to a larger one than to their individual clusters, which can lead to inversions. Complete, average, and centroid are definitely the most popular types of linkage. Note that the final dendrogram highly depends on the linkage. As you can see here, average and complete are pretty similar, but with single linkage, the dendrogram is quite unbalanced, and that's why this method is not used often. You can also see the individual observations being merged into larger clusters. So that's it for the theory. Let's get coding now. Let's apply what we learned in Python now. These exercises are available as examples on the scikit-learn website. I am simply reworking them a bit or explaining them here. The links are in the description, and the complete notebook on GitHub is also in the description down below. So we'll start off by importing some libraries. We will need NumPy. We'll also need matplotlib.pyplot as PLT. And finally, from scikit-learn.utils, we will import shuffle. So let's kick off this tutorial with a clustering. We will do color quantization with k-means, which is a technique to reduce the number of colors of an image while keeping the integrity of the image. So to do that, we will need from scikit-learn.datasets import load_sample_image, and from scikit-learn.cluster we will import k-means. Now, after importing our libraries, we will load the image of a flower. So the flower will be equal to load sample image, and we will pass in the name of the image. In this case, it is flower.jpg. Now we need to convert to floats and divide by 255, because colors are expressed as RGB, right? Red, green, and blue, with values from 0 to 255. So we need to normalize that so that the image displays correctly with matplotlib. So this is what we are doing here. So we convert to floats and we divide by 255 to normalize everything. Finally, we can show the image with plt.imshow, and we pass in flower. Now I have made a mistake here. The name np is not defined. That's because I did not import numpy as np. Sorry about that. So after rerunning this cell and rerunning this cell here, we finally get the picture of our flower, and this is what you should get. Now we will change the image to a 2D matrix. So width, height, and depth will be equal to original shape, which is the tuple of flower.shape. Here, d is the depth, will be 3, because as I explained earlier, each layer will correspond to either red, green, or blue. So 3 values in this case. And now we reshape it. So image array is equal to np.reshape flower, and then we'll reshape with the width times the height, and the other dimension will be the depth. Awesome. Now we will reduce the number of colors to 64 by running the k-means algorithm, where k will be set to 64. So our image sample will be equal to shuffle the image array. We'll give it a random state equal to 42 so that the results are constant whenever we rerun the cell, and we'll take the first 1000 samples. Now we will fit the k-means algorithm. And we set here the number of colors. As I said, this will be equal to 64. Then k-means will be equal to k-means. So we initialize the model. We pass in the number of clusters, which is the same as the number of colors in this case. And again, the random state equal to 42, because as you know from the theory part, k-means starts by randomly assigning each observation to a cluster. So we keep the random state equal to 42 to give the same results every time. And then we simply fit the algorithm. Then we get the indices for each color for the full image. That will be useful when we need to reconstruct the image, right? So each pixel in the 2D array will be assigned to a certain cluster, and that will help us to bring back the color and rebuild the image. So it's simply the labels, which is the prediction from the k-means. Now we need to write a function to rebuild the image. So like I said, each pixel is assigned to a cluster, which corresponds to a specific color. So we define reconstruct underscore image, and we will need as parameters the cluster centers, we will need the labels, and we pass in the width and the height of the picture. So D will be equal to the cluster centers dot shape, and we take D at index 1. Then the image will be simply an array of zeros in this case, and the shape will of course be the width, the height, and the depth. The label index will start at 0. And then for I in the range of the width, and for j in the range of the height, we write that image at index ij, so this is the coordinates in the 2D matrix, will be equal to the cluster centers at labels, and that itself will be at the label index. And then we increment the label index, so plus equal 1. And finally, we return the reconstructed image. So that's it for this function. Now we are ready to display both the original image and the reconstructed one with only 64 colors. So the first plot will be the original image. So we'll turn off the axes, and then plt.title will be the original image with 96,615 colors. And then we will show the original image, which in this case is simply flower. And now our second plot, so plt.figure2. Here we will display the reconstructed image. So again, turning off the axes, the title will be here we will write a string. Actually, we'll pass in a parameter in this string, so reconstructed image with n colors, because you can change the number of colors. We will do that after. And then we show the reconstructed image. So in there we will pass in our function reconstruct image, and you pass in k-means dot cluster underscore centers underscore. Pass in also the labels, and you pass in the width and the height that we defined earlier. And you get the following result. So as you can see, the integrity of the image is kept. Actually, the flower itself is very similar. I would say that only the background is very different. So let's go above and change the number of colors just for fun. So let's say we want only 4 colors. So rerunning these cells, as you can see now with 4 colors, the image is very different. But you can see it's almost like an artistic effect that you can play around with. So feel free to play around with this number of colors with yourself. Now let's work with PCA for dimensionality reduction. Here we will work with the iris dataset. This dataset has 4 features about 3 different kinds of iris flowers, and our goal is to visualize the dataset in 2 dimensions. So from scikit-learn.datasets we'll import load iris, and from scikit-learn decomposition import PCA. Now let's load the iris dataset. So iris will be equal to load iris. The features is iris.data. The target is iris.target. And then the labels or target names here is iris.target underscore names. Awesome. Now let's initialize the PCA algorithm, and we will specify that we want only the first 2 principal components since we want a 2D plot. Then x_r is PCA.fit x.transform x. Now let's actually print out the amount of variance that is explained by each principal component. So the explained variance ratio from PCA, and you can extract this information from the PCA object itself. So it's PCA.explained underscore variance underscore ratio underscore. Running this cell, as you can see, the first principal component explains 92% of the variance and the second one 5%. So that means that a total of 97% of the variance is explained with only 2 components. So now we are ready to plot our data set in 2D, and that data, that newly transformed data, contains about 97% of the variance of the original data set. So here we'll just specify 3 different colors to distinguish between the 3 different kind of iris flowers. So the final one will be FFA 600, and we'll set the line width equal to 2. Then plt.figure, and then for color in so for color, target name in zip, and we pass in colors. We will pass in 0, 1, and 2, and we pass in the target names. So 0, 1, and 2 here are simply the classes, right? So we'll draw a scatter plot. So plt.scatter xr when y is equal to I and 0, and then xr when y is equal to I and 1. So this is basically the x-axis and then the y-axis. And the color will be equal to the color at this point in the loop. Alpha will be equal to 0.8, and then LW is set equal to LW that we specified above. And finally, the label will be equal to the target name at that specific step in the loop. Now we will simply put a legend on our plot. The location equal will be equal to best. and we don't want any shadow. Finally, let's set a title to our plot. So PCA of iris dataset. Running this cell, as you can see now, we get this plot right here, and so you can visualize in 2 dimension a dataset that contained 4 features and 3 classes. So now you could follow up with some classifier, maybe decision trees on this transformed dataset to classify each kind of flower. Alright, so that's it about unsupervised learning. I hope that you learned something new, and if you did, please give a like to the video. Also, subscribe to the channel as I have way more content coming up, and we'll move on to more advanced techniques later on. Stay tuned.